Bismillahirrahmanirrahim. In this lecture, we will see the strain energy function, and we will derive the strain energy mathematical relation for strain energy function, and also we will discuss the symmetry of elasticity tensor, pairwise symmetry of elasticity tensor. After that, some stability conditions will be discussed, and at the end we will see the symmetry of material. Let's start with the strain energy function. To deform any material, any elastic material, we have to use the energies. So energy will be expended to deform any material. So elasticity says that a large part of this expended energy is stored within the deformed material. That is basically stored as potential energy. The stored energy is basically the potential energy. And after the removal of force, this stored energy, this potential energy, helps the material to come back into its original shape. Now, for elastic continua, we assume that all the expended energy is stored within the strained continuum. We refer this energy as the strain energy, and the mathematical expression corresponding to this strain energy is called the strain energy function. This energy is basically the physical entity. So as we have assumed that all the expended energy is stored within the strained continuum, so it means that we are dealing with conservative system. Now we have to formulate the expression for this strain energy. So for this for the conservative force, we know that if force is conservative, then curl of that force is equal to 0. When F is conservative, then curl of F is equal to 0, and when this happens, then we can write this F is the gradient of any potential function. Say it is V. So we can write this F is equal to V. From this we can write this component. This is any ith component of this F. As we have written F as the gradient of V as the potential energy function, then any ith component of this force can be written in terms of this potential energy function as F is equal to partial V partial xi, because F is equal to partial V1 partial V partial x1 E1 plus partial V partial x2 E2 plus partial V partial x3 E3. So ith component can be written as Fi partial V partial xi partial V partial x1 partial V partial x2 partial V partial x3. These are the three components respectively. No, by analogy we can write this thing in this way. How we have written this? For F we have written stress, because in our stress generation we have Tij is equal to Cijkl Cijkl Skl. T is for stress and S for strain. So here we will use the same thing, as F is equal to Kx, or basic Hooke's law, and Tij is equal to Cijkl, Skl is the generalized Hooke's law. When we will compare these two, we can see that T corresponds to F and S corresponds to X. So we can write this thing as instead of f we can write Tij, and instead of this x we can write Sij, and for v here we will use W, which is the strain energy function, potential energy function. This is what we have to derive its mathematical form. That what is the mathematical form of this W? Now we have this equation from this, and this is from here, and this thing is coming from this curl cross F is equal to 0. And why this is? Because we have conservative force and we have conservative system, and from where that conservative system has come, because we said that we are dealing with conservative system because we have supposed that all the expanded energy is stored within the continuum. Now we will move further with the help of this equation, and this equation, now you will see that this equation will tell you that how your elasticity tensor is pairwise symmetric. Up to now we have seen that our elasticity tensor, which has basically 4 indices, fourth order tensor, is symmetric in first pair and in second pair. And you have seen that after the implementation of this symmetry in first pair and in second pair, we have 36 independent components, and in last lecture we have also written those 36 components very easily with the help of second index, with the help of 2 index notation. Simply we can write those 36 components in the form of a 6 by 6 matrix, and from that 6 by 6 matrix you can easily have the number of independent components, 36 independent components, and from that 36 independent components you can write all other dependent components, which are 45. Now further we will see that whether we have some more symmetries which will reduce the number of independent components of this elasticity tensor. So this will happen with the help of this equation. Let's see how this equation will help us in reducing the number of independent components for elasticity tensor. So I have written this again. You can write Tij is equal to Cij KL SKL, and now you can differentiate this equation both sides with SKL. So it will be partial square W, partial SKL, partial SH, and right hand side we have Cij KL. Now you will interchange Ij and KL pairwise. That you are writing instead of Ij KL and instead of KL Ij on both sides of one, and then you will have second equation. And continuity, and we know that W is a energy strain energy function. This is continuous, and it has second, all the derivatives, partial derivatives are continuous. So due to all the continuity, we have this thing, like you have seen that partial square f partial x partial f partial y equals to partial square f partial y partial x. F is continuous and its derivatives are continuous, so you can use that. It means that if this is happening, so we can write from 1 and 2 this thing. Now you can see that you have obtained the pairwise symmetry of this elasticity tensor, which you can see Cij KL equals to CKL Ij. Like if you can write Ij alpha KL beta, then it would be C beta alpha. So this thing is telling that your elasticity matrix is symmetric along the main diagonal. C alpha beta equals to C beta alpha. I think where in previous lecture we have written Mn instead of alpha beta, where we have used Mn here, and here we are using alpha beta. It nothing matter. You can use alpha beta or Mn, whatever you want to use. So this is alpha beta or Mn. So if this is symmetric, so it means that these 36 independent will be reduced to 21 independent, because you have total 36, 6 in the diagonal and 15 above and 15 below the main diagonal. So 15 plus 6, 21. So you have 21 independent components. So we have reached at the 21 independent components of that elasticity tensor, which has basically 81 components in total. Like stress and strain tensor, they have 6 independent components but total 9 components. In the similar way, for elasticity tensor, it has 81 components but it has 21 independent components only. That if you know the 21 components, then you can write all other 60 components to obtain total 81 components. So it means that to get all the components, you need only 21 components, independent components. Know the explicit expression for the strain energy function W. Now this is written from that equation. This equation we have simply written this thing. Like in your differential equations, that you usually write df dx equal to x, then you can write df is equal to df and x into dx. So we have written this thing, dw is equal to, this is tij, instead of tij we have used cij k scale dsij. Now we will change the I and j, ij and k like this, and this can be written in this way because we have seen above that this is symmetric. So adding 1 and 2, you have this, and this can be written in the differential of these two. Now take the integral on both sides, we can have this. So this is the expression for the strain energy. This is the mathematical expression for the strain energy, and you can see that these Cij, K are basically the elastic constants. You know that this is the elasticity tensor, and these are the elastic constants of the material. Like F is equal to Kx. What is K there? K is the elastic constant, and usually you used to say that this is the spring constant. Like these Cij, K are the constants for particular material, and their values are fixed for any particular material. After this we will discuss stability, and after stability we will go for the symmetry, in which you will see that you have different types of materials, different types of continuum depending upon the symmetry. The symmetry will make different kinds of continuum. So it means that if these are constant, then it means that your strain energy function is only depending on strain, as its name, strain energy function. So it must depend on only S strain. So you can see that it is only depending on S. So for unstrained state, that when we have no strain, so W must be 0. So this is 0. Otherwise, in general, this is positive. Energy is positive. So this is the mathematical expression for the strain energy function. Now the stability conditions. And we have seen that our strain energy function is formulated in terms ofCijkl. So this strain energy function provides some basic restrictions on these parametersCijkl, and these restrictions, constraints, are called the stability conditions. That due to this strain energy function, some basic conditions, some basic constraints must be followed by this elasticity tensor. So in general, energy is positive and it is 0 only for undeformed continuum, undeformed state. As we have seen that for undeformed state we have S0, that we have no strain, we have no change. So for unchanged system continuum we have W0, otherwise W is positive. So it vanishes only when you have no strain. So we have this expression. You can write this thing in this matrix form. This C is for this, and this is the matrix form of this. This is a transpose of S. This is S. Yeah, this is 6 by 6, and this is 6 by 1. This is 1 by 6. This is 1 by 6 order. It has 6 by 6 and it has 6 by 1. So we have only at the end one number scalar, which has single number. From there you can see that all the indices are dummy. So you must have at the end one number. So this is the mathematical form, matrix form of this. Now as W is greater than 0 positive, so this is positive. When this is positive, when we have this, and this thing is telling that C is positive definite. C is positive definite. This is the definition of positive definiteness of any matrix. You can see this thing from your basic linear algebra, that what is a positive definite matrix, where you can see that X transpose AX greater than 0. So this thing is telling that C is positive definite. So it means that your C must be positive definite for W is positive, and this is the stability condition on C. And with the help of this positive definiteness of C, you will see that you will have different types of condition on these parameters. So you can write that C is positive definite if and only if this is positive. Now we will take help from the linear algebra, some results of the linear algebra. A real symmetric matrix is positive definite if and only if the determinants of all its leading principal minor, including the determinant of the matrix itself, are positive. If we have C, symmetric and real, and if it is positive definite, then all the leading principal minors, including the determinants of the matrix itself, must be positive. This thing is written here. This is C110, C1, this 2 by 2 determinant of 2 by 2 matrix. This is 3 by determinant of 3 by 3, then 4 by 4, then 5 by 5 by 5, and then at the end whole matrix determinant of the whole matrix must be positive if C is positive. And we know that C is positive, that if W is greater than 0, then C is positive definite, and C is positive definite. When C is positive definite, we have this is from the result, this is from the linear algebra, result of linear algebra, that when your matrix is positive definite, then you have all the determinant of its leading principal minors, and you have 6 leading principal minors. First element C11, second is coming from the 2 by 2 matrix, which includes C11, C12, C12, C22. It's determinant positive, then this, then up to so on. The determinant of the whole matrix is positive. No, second result says that if your matrix is positive definite, real symmetric matrix is positive definite, then all its eigenvalues are positive. No, like this, if this determinant is positive, then you have condition C11, C22 minus C12 square must be positive. This is the condition, that your product of C11 and C22 must be greater than square of the C12 square, C12 square of the C12. This is the condition on the parameters. And like after solving these determinants, you have different types of conditions, different type of constraints on these parameters. So similarly, if you can have the eigenvalues of this matrix, then they should all be positive due to positive definiteness of this matrix. So your eigenvalues of this matrix C will be in the form of all these parameters, there should be any products sum of these parameters for eigenvalues, so they should be greater than 0. Then you can have different types of constraints with the help of these eigenvalues. So these are all the stability conditions. The one thing more, let's see what happens with this CMM. CMM means all the diagonal components. W is equal to this, you can choose one S as 1 0 0 1 0 0, and you will have only C1 1. As W is positive, so C1 1 positive. Similarly, you can have C2 2 positive, C3 3. So it means that if W is positive, which is positive, all the diagonal components are positive. So it means that we have different types of stability conditions. Diagonal components are positive, and you can have some expressions with the help of these determinants, they should be positive, and also expressions in terms of the eigenvalues in the form of eigenvalues. Those expressions can be obtained from the eigenvalues of the C, and they should also be the positive. So all these will give you the stability conditions, and these are the constraints. So these are the stability conditions for the elasticity tensor. No, symmetry. Symmetry is basically the transformation under which an object remains invariant. That you have y is equal to x square, then transformation, if you apply the transformation y is equal to change y to y and x to minus x, then you will have again the y is equal to x square. There is no change on that equation. So this transformation, this transformation is will work as a symmetry transformation for this y is equal to x square, that is symmetric along y axis. You can see with the graph y is equal to x square, and you usually use to say that this y is equal to x square is symmetric along this y axis, and transformation is behind this is y, change y to y and x to minus x. So this is the meaning of this thing which is written here, that it is a transformation under which an object remains invariant. Now we will have to go for the symmetry of container. And what does the symmetry of the container means? We know that for any container we have the elasticity matrix C, which has all the elastic parameters C11, C12. They represent the elastic properties of that particular material. Like you say that K represent the constant, K is the spring constant, in such a way that C11, C12, all these represent the elastic properties of container. If your C is invariant under any transformation, and you apply the transformation on that C, and you will have again, and you will have a matrix C dash, and if C and C dash is same, then that transformation will act as a symmetry transformation for this matrix C. So if this matrix C is if this matrix C remains unchanged due to this transformation, then it means that the continuum which has this matrix C must has the symmetry. Now we have different types of symmetries, n-fold axis of symmetry. An axis, this is the definition of n-fold axis of symmetry. An axis such that a rotation of theta angle is given 2 pi by n about the axis leaves all the properties same, or if we rotate through 2 pi by n, the components of tensor that describe the materials remain same, then that axis is called the n-fold axis of symmetry. That we are taking the rotation about a particular axis with an angle of 2 pi by n, and we have no change in the components of tensor which represents the material, like C. C is the tensor which is representing the elastic properties of the material. Then that axis is called n-fold axis of symmetry, and angle of rotation must be this 2 pi by n. It means that you can have 1 fold, 2 fold, 3 fold. So angle will be changed with this n, 2 by 3, 2 pi by 2, 2 pi by 3. And that axis is called n-fold axis of symmetry. This is the definition of n-fold axis of symmetry. See, like that we take the rotation. If we are rotating the system about x3 axis with some angle. In the similar fashion, we are saying that we are taking the rotation about an axis with an angle of this, and if the properties will not change, properties of material, properties of that tensor which represents the material will not change, components of tensor which represent the material will not change, then we will say that that particular axis is the n-fold axis of symmetry for that material. This will be more clear when we will go further and discuss different types of continuum. This is the usual definition of plane of symmetry. If you have this type of transformation, it means that you are talking about xy plane as symmetry plane. And this is the reflection through origin. You can y is equal to x cube, y to minus 1, y x to minus x, then then you will again have y is equal to x cube. That transformation y minus y, x minus x is a symmetric transformation for y is equal to x cube. Now, due to this symmetry of continuum, you will have different types of material depending on the symmetry. No, keep in mind that we are not going to find any symmetry for the material. We will discuss materials with symmetries. These are given that if we have these types of symmetries, then we will have that material. I will tell you the different types of material which will have different types of symmetries, and we will not find those symmetries. We will only see that if you have this symmetric axis, x1 axis, x2 axis, x3 axis, then you can have this type of material. These all are defined things. We will not find any symmetry. We will only make use of those symmetries, and by making use of those symmetries, we will see the components of C, matrix C. This is one example of symmetry, that if you have that there is a plane of symmetry, choose axis so that x3 is the normal to this plane, that x1 x2 plane as symmetry plane, then you can write this transformation: x1 dash is equal to x1, x2 dash is equal to x2, and x3 dash is equal to minus x3, and transformation matrix is this. Now we have a material which is we have a material for which we have second rank tensor, this epsilon ij. This tensor is representing the properties of material. Now, if we will see, we are saying that this transformation is a symmetric transformation for that for this material, then it means that the tensor which representing this material will not change. Components of this tensor will not change, as we are seeing here. The components of tensor will not change. Here, components of tensor that describe the material will not change. And we have said that this material for which we have this tensor which represents the properties of that material has this transformation as symmetry. So under this transformation, this tensor, the components of this tensor will not change. What does this mean, that components of this tensor will not change? That epsilon ij will be equal to epsilon dash ij before and after transformation. Ij is before, epsilon ij is before transformation, epsilon dash is after transformation. Like that, you can write, you usually write T dash ij is equal to q pi q pi q l j t q l. That this t q l is the components of t before transformation, and t dash ij are the components of the same t after transformation. So they, if the transformation is a symmetry transformation, then t will be equal to t dash. And here we are saying that this transformation is a symmetry transformation, so epsilon ij will be equal to epsilon dash ij. That components will not change. Like here we have said c is equal to c dash, epsilon dash ij is equal to epsilon ij. Like this, that components of tensor will not change if we have symmetry. Similarly, when we will use this n-fold axis of symmetry, we will say that if this material have this fold axis of two-fold axis of symmetry, three-fold axis of symmetry, then components of the tensor which is representing this material will not change. And we will say that, and we will see that what is our main purpose. Our main purpose is to see that how many number of independent components can be reduced with the help of symmetry. With the help of symmetry. That, for example, y is equal to x square. You can have x, when x is equal to 2, you have y is equal to 4. And when x is equal to minus 2, you have again y is equal to 4. So you can see that for 2, 4, you have 4, and for minus 2, you have 4, and no change, because your y is equal to x square is symmetric about y axis. That you have same 4 for x equal to plus 2 or x equal to minus 2. Like here we will see that epsilon ij is equal to epsilon dash ij due to this symmetry. And let's see how many independent components can be reduced. That if you have one side of the curve y is equal to x square, then you can have similarly second other side for that graph of y is equal to x square. That's simply the image, and no change. Let's see what happens with this. So how many components would be reduced. This is thus 2 by 2 3 by 3 matrix for this tensor. You have 9 components, and we have to check these 9 components. This is the definition of transformation. This is the transformation law for this second order tensor. Simple. And this is due to symmetry, as I was saying. This is due to symmetry, that we have said there epsilon I, that this material has symmetry of this symmetry of this plane, about for this plane, that this plane is acting as a symmetric plane for this material, and the tensor which are representing this material is epsilon ijk. So its components will not change. Epsilon dash ij will be equal to epsilon ij. Epsilon dash 1 1 will be this. You have written ij 1 1. Expand the summation on pq. It will be a11 epsilon 1 1 plus a21 epsilon 2 1 plus epsilon 3 1 a3 plus a31 epsilon 3 1, and second and third terms are not written here because these a1, these are the components of this matrix, this transformation matrix. This a11 a12 a13 a21 a22 a23 a31 32 33, and you can see that only diagonal components are not equal to 0, all others are 0. So that is why second and third terms are not written, because they are 0. They have a21 and a31, and because of a21 and a31, second and third term will be 0. Now what is a11? A11 is basically 1 1, so epsilon dash 1 1 is equal to epsilon 1 1. So no effect on epsilon 1 1. Epsilon 1 1 remain epsilon 1 1 after transformation. That epsilon 1 1 dash equals to epsilon 1 1. No effect on 1 1. 1 2 dash. This is 1 2 dash. Again no effect on epsilon 1 2. 1 3 dash. No, you have minus epsilon 1 3. No, this is equation, and use this symmetry. Epsilon 1 dash 1 epsilon dash 1 3 is equal to epsilon 1 3. This is from this. Epsilon dash 1 3 is equal to epsilon 1 3, and using the transformation law, you have epsilon dash 1 3 is equal to minus epsilon 1 3. Now from this and this, you can see that epsilon 1 3 is equal to minus epsilon 1 3, and epsilon 1 3 is 0. So using this transformation, your epsilon 1 3 becomes 0. Similarly, your epsilon 3 1 becomes 0. Now we will check 2 3. You have this. Again you have minus. So, and again from these two, epsilon dash 2 3 is equal to epsilon 2 3 due to symmetry. So from this you can write epsilon 2 3 is equal to minus 2 3. It is minus 2 3 0. So epsilon 2 3 0, and also epsilon 3 2 0. So we have, after the application of this symmetry, you have 5 components only. 4 are 0. So it means that you need only 5 components to have all the components of this epsilon, to have all the properties of the material. So for that particular material which has this symmetry, that which is xy plane, then that particular material needs only these 5 components to represent its properties.